Hey everyone, so this article I found is from scientists at UC Irvine and Los Alamos National Labs from 2017 and is the first identification of a formal 2 plus oxidation state on plutonium and the characterization of that 2 plus compound. At the same time, they also accomplished the first structural characterization of a plutonium carbon bond, and that compound is what they used as a precursor to this 2 plus compound here. So chemistry like this is important because knowing the extensive oxidation states of the elements gives pretty good insight into their chemical behavior as well as their physical properties. And in this case, they wanted to look at plutonium specifically because previous to this, it was found that uranium 2 plus and thorium 2 plus complexes showed 5F361 mixing or electron configuration for the uranium 2 plus, and the thorium 2 plus showed 5F062. And because of this, they wanted to know, first of all, whether a 2 plus plutonium compound could be stable and isolated, and second, whether this compound would show any 5D mixing like the uranium and thorium compounds did. So they mentioned that lanthanum 2 plus, as well as the uranium 2 plus compounds, were first made by reducing organometallic complexes with metals starting in the 3 plus oxidation state. And so they tried to do the same thing here using a potassium cation in a 222 cryptand, which they just call crypt. And an image of that is seen over here, just to kind of give you an idea what that looks like. So the 222 comes from the two oxygens on each of these bridges. And since there are three twos, you have three bridges. And then here would be your potassium cation in the middle. And so in addition to this, they wanted to attach these trimethylsilyl substituted rings as ligands onto the plutonium, both in the 3 plus precursor and in the 2 plus final product, which they call, or for the rings, they call it CP double prime there. So for their synthesis of the 3 plus precursor, they have that here. So they started with plutonium metal, and then they oxidized that in iodine, or with iodine in diethyl ether, and then followed that with a few rounds of the potassium CP double prime, and that gave them this plutonium 3 plus CP double prime, which is basically the same as this over here, except it's a 3 instead of a 2 on the plutonium. And they say that they were able to confirm the presence of the 3 plus CP double prime with X-ray diffraction, or XRD, and 29 silicon NMR, but the high levels of disorder in the compound prevented measurement of, they say, metric parameters. I'm assuming that might mean something like bond lengths. But once they were able to isolate the 3 plus compound, they were able to reduce that plutonium further with the addition of potassium graphite there, and adding the empty cryptand in diethyl ether again. And so this on the right is their final plutonium 2 plus product, and these are the big CP double prime rings that they mentioned earlier. And so the presence of this final compound was also confirmed with hydrogen NMR and XRD. They did note that the 2 plus compound decomposed extremely fast, so within minutes, and even when triply contained or encased, here they say inside a glass capillary nested in an NMR tube liner and inside of a glass NMR tube, onset of decomposition was observed within 20 minutes. So not a whole lot of time to characterize that. And so they found that the 2 plus compound was isomorphous with the previously mentioned thorium 2 plus, meaning that they have similar crystal structures, and shared a similar metal ligand coordination geometry with the lanthanum 2 plus compound. And then here they mention, I guess, the accuracy of their previously done computational work using density functional theory, where they say predicted the trigonal planar structure, the trigonal planar structures for the 3 plus and 2 plus compounds, which is this up here. So we have the 3 cyclopentadiene rings, and you have the plutonium in the middle, and they're all kind of coplanar in the center. And then for the electronic structure, they mentioned doing some Mulliken population analysis, which I'm not too familiar with. I don't know a whole lot about computational stuff, but it seems like, based on what I looked up, it involves a lot of electron density probability calculations. And so using this, they found that the HOMO here, highest occupied molecular orbital, was predominantly FZ cubed, but also showed appreciable, which I guess 7% is appreciable, DZ squared character. And so I kind of wanted to try showing this over here. They mentioned, or they had this image at the bottom in their supplemental info. And so here, up here on the left is the FZ cubed orbital, and on the right is the, the DZ squared orbital. And so you can see here at the bottom, it's not exactly one or the other. It looks kind of a mix of both. At least to me it does, because I would assume if this was completely FZ cubed, these rings up here would be shifted down a little. But it looks like this bottom ring is closer to the center, kind of how it is up here in the DZ squared orbital. And then this mixing, I think, kind of makes sense when they mentioned that there's a near degeneracy of these different configurations. A near degeneracy meaning that they have very similar energies. So I would think that means that since their energies are so similar, it's likely that one configuration isn't always favorable over the other, leading to the 6D mixing. So one thing that confused me a little here was they mentioned that some of their calculations suggest that the 5F or the 61 and 60 crossover occurs near plutonium, but they had previously, but there is that thorium 2 plus compound which showed 6D2 configuration. So thorium being 4 elements before plutonium, I'm not really sure why they say that the crossover occurs near plutonium. I would think it'd be better to see it occurs near thorium, unless there's something else that I'm missing here. So something else that they did to confirm the presence of the 2 plus compound versus the 3 plus was the use of UV vis NIR absorption, which works by shooting photons in these respective energies at a substance and then measuring what wavelengths of light are, I believe, either scattered, reflected, or absorbed. So they mentioned seeing some absorption peaks that were assigned to Laporte forbidden 5F, 5F transitions as part of the 3 plus compound. And these, there's an absence of these found in the 2 plus compound, or if they were found, they were only as impurities in the solution phase, but not detected at all in the solid state spectrum for the 2 plus compound. And another thing to distinguish the 2 plus compound from the 3 plus were some very broad bands that they mentioned here at these specific absorptions, which they noticed were much more intense than any 5F, 5F transitions that were typically seen in that region. And then using time-dependent DFT calculations, they were able to attribute some of these stronger absorptions to metal-to-ligand charge transfer coming from the plutonium 5F orbitals. And they rationalized this transition, or this transfer, by saying that there was an increase in 5F orbital energy, likely caused by electron repulsion in while it's in the 5F6 configuration, versus the 5F5 configuration of plutonium 3 plus. Then they also state that some of their calculations suggest that the increased energy of the 5F orbitals compared to the more stabilized 6 DZ squared orbitals resulted in a lower energy 5F to 6D transition, and this increased stabilization of the 6 DZ squared orbital comes from, over here they mention Jahn-Teller distortion, which is where the structure of a molecule kind of stretches. So in this case, it would be stretching here along, use a different color, here, along the axis of the DZ squared orbital. And they're saying that that distortion is making that orbital more stable, resulting in the lower energy transition from 5F to 6D. And they mentioned that they need to do some more measurements and computational work to verify some of these claims, but I think this is a good start, a great start for just identifying the 2+ oxidation state of plutonium. And I think by now, we've confirmed by now that there's a 1+ state for plutonium as well. So I think we've got 1 through 7 for plutonium oxidation states. But yeah, I thought this paper was super interesting. That's about it. I know you didn't have a choice, but thanks for watching.